Hi, welcome to this lesson on linear regression. Regression analysis allows us to predict one variable from another, similar to the correlation analysis in the previous module. This holds tremendous potential for HR as it allows you to do numerous analyses that will benefit the company as a whole. For example, regression analysis allow you to predict turnover, or how certain initiatives such as training will impact your employees and your bottom line. These type of predictive analytics all start from the linear regression analysis, which is the topic of this lesson. So, let's get started. In the correlation analysis, you learned about how to use two continuous variables and measure Pearson's R to see what type of association the two variables have with one another. You could also measure R squared to understand how well the two variables could explain each other's variance. If you had a Pearson's R of 0.5, you had an R squared of 0.25. This meant that 25% of the variation in one variable is explained by the other variable. R squared can also be seen as the goodness of fit measure for linear regression models. The goodness of fit is the extent to which observed data matches the values expected by the regression line. With the linear regression, you always want to create a model that best describes the current data in a linear fashion. A linear relationship means that for every fixed change in an independent variable, a certain fixed change will occur in a dependent variable. For example, if the independent variable goes up with 1 point, then the dependent variable may go up with 0.25 points. An example is engagement scores. A company like Best Buy was able to predict that when engagement in a store goes up with 1 percentage point, revenue in that store increases with $100,000. This is the kind of insight that a regression can create. If your regression model is able to accurately predict the dependent variable based on the independent variable, your model will have a high R squared. Let's see an example. Here you can see the relationship between age and salary. We have collected some data from our participants and plotted their points according to their age and salary per month. Next, we plotted our regression line. Back in our correlation analysis, this line was the same as the best fit line, and is the line that has the lowest average squared distances between all the data points. The distance between the data points and the regression line can be seen here. The lines that are drawn is what we call the error, which is how much our data points deviate from our regression line. For instance, at age 25, the distance is $300. This participant should be earning $2,750 according to our model, but in reality, he's earning $3,000. Similarly, we have a participant who should be earning $3,250 according to our model, but in reality is only earning $3,100. These differences, or errors, are then squared, and our model calculates the line that has the least squared distance between all the data points. Like I said earlier, this line follows a linear relationship. Linear relationships have the following formula. Y is ax plus b. Here, y is the variable that we want to predict, in other words, our dependent or outcome variable. A is the value we think our I will go up with if we increase our independent variable x by 1. This is also called the slope, coefficient, or, as in many statistical outputs, the beta. Don't confuse the beta output of the regression with the b in this module, which is our intercept. The intercept is the value we think I will be if the independent variable was nil or non-existent. If the independent variable had a value of 0, what would we reasonably expect the value our dependent variable to have? In our example of age and salary, we had a linear regression of I is 100x plus 250, where y is the salary per month and x is age. So in this model, every 10 years someone gets paid $1,000 per month extra on average. So when someone is 25, it's $2,750. When someone is 30, it's $3,250. When someone is 40 years old, it's $4,250. With this information, you can now predict what someone would make if they were, let's say, 50 years old or 60. However, if all our data followed this formula, we'd have a straight line. Unfortunately, it doesn't, as you can see. This is because we don't account for certain variables in our model, which would account for the error. These variables could be whether someone is a good negotiator, for instance, or his or her education level. The fewer variables you have in your model, the greater the error. However, we're not interested in these factors for now, which is why we call them error. The data in our model can be characterized by the following formula. The data is the model plus the error. The error is the degree to which your data points differ from the model. No matter what you do, there will always be some error in your data, as you can't account for every single factor in the world, nor would you want to. This would increase the complexity of your model, and it makes it difficult to gather all the data for future regression analysis. Thus, you will always have some error in your regression analysis. In regression analysis, we often use the standard error of the regression, or S. S represents the average distance that the observed values fall from the regression line. Smaller values are obviously better because they indicate that the observations are closer to the best fit line. The standard error of the regression is similar to the R-squared in that they both explain how good our models fit the data. Whereas R-squared shows how much one variable explains the other variable in percentages, the standard error of the regression shows in exact numbers how much we can expect a number to deviate from our model. In other words, how precise our model is. The relative percentage of R-squared, for instance, 76.1%, doesn't tell us how precise our model is. For that, it's better to use the standard error of the regression, which can tell us what we can expect our models to differ on average, for instance, 3 units from the model, which is not the precision we wanted, because we wanted to have a maximum of 2 units difference on average. Next, when performing a linear regression, we use the t-statistic to calculate whether the regression is statistically significant. In the next lesson, we'll use the f-statistic when we cover multiple regression. But because the linear regression only uses one variable to predict a dependent variable, we use a t-test. For this, we use the following hypotheses. The null hypothesis is a1 equals 0. The alternative hypothesis is a1 does not equal 0. The t-value is calculated by dividing the slope of the regression line with the standard error of the slope. This is quite complicated and is not something you need to remember. You can read the t-values and p-values from your statistical output and decide if you can safely reject the null hypothesis if your p-value is below the alpha value. This means that your independent variable, the slope, has a statistically significant effect on your dependent variable. This picture shows the output of a linear regression analysis. A sample of 33 companies was randomly selected and data collected on the turnover rate, percentage, and trust index, measured on a scale of 0 to 100. The trust index measured how much employees trust the company and their managers. To interpret this output, you will want to look at the beta at the top, and then the corresponding coefficient to the related variable. Remember, our formula is y equals ax plus b. Y is the turnover rate, and x is the dependent variable trust index. Here, b, the constant, is 12.1005, which means that when the other variable, trust index, is non-existent or 0, the turnover is 12.1%. Next, trust index has a beta, or coefficient, of minus 0.07149. This means that for every value of the trust index, the turnover rate would go down by 0.07149. This means we can calculate our formula of y equals ax plus b. Y is turnover rate, a is minus 0.07149, x is the independent variable trust index, and b is the constant or intercept, which is 12.1005. In total, our formula is turnover rate, percentage, equals minus 0.07149 times trust index plus 12.1005. Now we can predict the turnover rate for a certain company when we have that trust index. Let's say you find another company and collect the data on the trust index. You find out that this is 50. What does this model predict the turnover rate will be for this company? Pause the video, take a few seconds, and then I'll give the answer. The formula to predict the turnover rate for this company is turnover rate percentage is negative 0.07149 times 50 plus 12.1005. which equals 8.526%. So the turnover rate for this company is, most likely, 8.526%. Furthermore, you see that our R-squared is 79.6%. This means that our model is able to account for 79.6% of the variability in the dependent variable, turnover rate. You also see the adjusted R-squared, but this is something you'll learn more about in the next lesson. Furthermore, you can see that S, or standard error of the regression, is 1.497. This means that, on average, turnover can differ 1.497 points from our predicted scores. It's up to you to decide whether you think this is accurate enough. Do keep in mind that this is a specific sample of companies. This statistic likely doesn't apply one-on-one everywhere in the world, as turnover rates and turnover habits and behaviors will differ across geographies. Doing this analysis for your own company helps to create a more accurate model and a better prediction. Finally, let's take a look at the 5 assumptions for the linear regression analysis. You can perform this linear regression analysis if, first, your dependent variable needs to be on the interval or ratio level. Second, the relationship between the independent and dependent variables is linear. You can test this by looking at the scatter plots of your data. Next, you can't have any significant outliers, as your regression analysis is sensitive to outlier effects. Remember Anscombe's quarter? The bottom 2 pictures are regressions that are completely misconstrued due to the outliers present in the dataset. Fourth, all variables need to follow a normal distribution. The last assumption of the linear regression analysis is homoscedasticity. The variance of the residual in your analysis should be constant across your predictive variable. This means that the predictive power of your regression analysis should be equal from low levels of the x value to the high levels of the x value. A scatter plot of the z predictor on the x-axis and the z residual on the y-axis is a good way to check whether the data is homoscedastic, meaning the residuals are equal across the regression line. If your data does not have the same error across your regression line, the predictive power of your linear regression will differ when trying to predict your dependent variable according to certain x values. For instance, your regression analysis might be really predictive at low levels of the independent factor, but not predictive at all when you look at higher levels of the independent factor. This cannot be, so you must make sure that your data adheres to homoscedasticity. We will put a resource about this in the reading material. Once your data adheres to these assumptions, you can perform your regression analysis. And that's it for this lesson. In this lesson, you learned more about the characteristics of a regression model. Next, you learned about regression to the mean. Third, you learned how you can test your regression model, and finally, you learned about the assumptions that your model needs to adhere to. In the next lesson, we will continue with the regression analysis, but this time we will focus on multiple regression, a more complicated version that's very similar to simple linear regression. See you there.